Well guys, let's answer the question, is the square root of all primes irrational? Now if you think about it, the answer is obviously yes. But let's prove it. Let square root of n be represented as a ratio. That means we're going to be doing a proof by contradiction. So let's square both sides. Now I have let square root of n be expressed as a ratio of p's to q. And here p and q are co-primes, meaning that their GCD, their greatest common divisor, is 1. So basically this means p by q is in their simplest form. It cannot be reduced further. That is our first condition, or just our main condition, and p and q are both integers. So n square, or not n square, n is equals to p square by q square. So we can rewrite this as q square equals to p square by n. And here, if p square divides n perfectly, and here p square does in fact divide n perfectly because it produces q square, and since q is an integer, q square must also be an integer. So if p square divides n, then p must also divide n. Since n is a prime number, n's factors are 1 and n itself. And for our square or number square to divide a prime number, the number itself must also divide that prime number. But it's not true for composite numbers, because let's just take 4. Its factors are 1, 2 and 4. So here 2 makes this number not prime, and here 4 divided 4 is obviously 1. That means here 4 divides 4 perfectly to give 1. 4 divides 4 to give 1. And right here we can express 4 as 2 square. So 2 square divides 4 completely. But that does not mean that 2 divides 4. But it's not the case with prime numbers, since its factors are only 1 and n, and there are no other factors in between. So we can rewrite p in terms of n. So we can write it as n into some number, let's just say a. So right here we get q square is equals to na square by n, which is n square by a square by n, and we have q square is equals to na square. And again, similar to this, we can rewrite it as a square is equals to q square by n. And we have a similar property to that with the q. Here we also have that q square divides n. That means q must also divide n. We can rewrite q in terms of n again, n into b. So we see that p is a multiple of n and q is also a multiple of n, which means that both of them are divisible by n, but that breaks our first condition, that their greatest common divisor is 1. However, with this proof, we can see that p and q both have the greatest common divisor of n. So p and q are divisible by n, so which means that the first condition, p and q are co-primes, is contradicted. Which means, finally, square root of n is irrational by proof by contradiction. Because here we have contradicted a condition over here, and since n is just any prime number, that means that the square root of all primes is indeed irrational, no matter which prime number it is. If you learned something new, please like and subscribe. Thank you.